Hello, welcome to a video on section 8.2 regarding graphs of simple rational functions. So before I get into what is a simple rational function, let's review what we talked about in 8.1, which is regarding direct and inverse variation. Where direct variation follows this pattern, y equals k times x, whereas inverse follows this pattern, y equals k over x, where k is the constant of variation. So it's going to be a number that we'll put into the equation, and that kind of stays with that number. You could use letter A. That's what we use in some of the notes in 8.1. The letter used for the constant doesn't really matter. Just know that it's a constant. And remember, direct variation is when you have a constant ratio to y over x, whereas inverse variation was when you had a constant product, so x times y. So if I look at my ratio here, y over x, I get 5, 5, 5, 5. That's going to be direct. And in fact, the equation would be y equals 5x if you were to plug in one of those pairs for x and y into y equals k times x. Here, we'll use different colored blue. If you make a column of the product of these, you're going to get 6 every single time. So this is what we call inverse variation. And the relationship will be y equals 6 over x. If you were to plug in 6 for y, 1 for x into this formula right here and solve for k, you would get 6. So that's basically what we see happening with that one. Now, if you look at example 2, that's the same thing as what we got from the table for part B of number 1. So this is actually what we call a simple rational function. It's rational because it's a ratio of two expressions, one expression being 6, the other being x. If I just plug into the table, pretty easy, I get -2 and -3, -6, that's undefined. Let me write that out actually, undefined. And then 6, 3, and 2. Let me actually erase that, make that a little more neat. So you can't plug in 0, obviously. So I'm going to plot my points, -3, -2, which is right there, -2, -3, right there, -1, -6, right there, 1, 6, right there, 2, 3, right there, 3, 2, boom. Now, how are we actually going to graph it? The graph is going to look like this, and I'll explain why in a little bit. I'm going to draw these boundaries here. So this right here is our horizontal asymptote, or we call it end behavior asymptote. That right there we're going to call a vertical asymptote, or we like to call it an infinite discontinuity. Oh, let me write that more neatly. Infinite discontinuity. Okay. So that's going to happen at x equals 0 for the vertical asymptote. I'll call it VA for short. And the horizontal asymptote, I'll call it HA for short. That would be y equals 0. Now, why do these exist? This is going to be a Google form question, so please take it as I'm going to create a new sheet here. Why vertical asymptote at x equals 0? Why horizontal asymptote at y equals 0? Okay, so why are these things happening? Now, don't say because we can't have 0 in the denominator. That's true, but it's not the real reason why. Here's the correct way. As x gets close to 0 on either side, so basically from the left or the right, y approaches positive or negative infinity. That is the reason why we have vertical asymptotes. So let's look at the graph. Here's the graph. So notice that if I get close to x equals 0, I'm going to trace in yellow from the left side or from the right side. Either way, I'm having some sort of infinite behavior with y. Y is going towards positive infinity up here, or y is going towards negative infinity down there from the left side. So as I get close to 0 for x on either side, we see that y is shooting up or shooting down towards positive or negative infinity. That's the reason why we have vertical asymptotes. Now, for horizontal asymptotes, don't say because y can't equal 0, because actually it could for some cases. So in this case, obviously y is not going to equal 0 because you're doing 6 divided by x. For y to be 0, the numerator has to be 0. But remember, our numerator is a constant at 6. That's part of the inverse variation situation where your numerator is a constant. So obviously that's not going to happen, so we're not going to get 0, but that's not the real reason why. The real reason why, this is the correct way, as x approaches positive infinity or negative infinity, so basically that's going to be the right end if you're going towards positive infinity for x. Negative infinity would be the left end, right? For negative infinity for x. As x approaches that, y approaches a particular number. In our case, for this example we just did, and I'll do this in green, as I go forever to the right or forever to the left, what's y approaching? Y is approaching 0. So essentially, the ends of the graph of y equals 6 over x is getting closer to 0. So it behaves like y equals 0. So the graph itself, if you actually were to graph in the calculator y equals 6 over x, and just change the window and focus like on when x is like 10 or 20 or 50 or whatever, it's going to really look like a horizontal line. It's not one exactly, but it looks pretty close to one. So that's kind of what's going on with the exploration here. Well, actually, that's not quite what's going on with the exploration here. But if you do different scenarios like that, or that, or that, or that, all you're really going to notice is that the graph kind of gets stretched. That's really what's happening. The graph gets vertically stretched. Domain and range. Domain is going to be all real, but 0. Range is going to be all real, but 0. And that was actually true for example 2. We didn't really talk about that. Between these two, that's a reflection 2 over x, because you have the negative out in front. The main range, still the same thing, all real but 0. Range, all real but 0. Again, just look at the graph. The domain's pretty obvious. We know we can't plug in 0 for x because we can't divide by 0. And for the range, we just see that y doesn't equal 0. Now let's do some translations. So you have h and k, which is the same as before. H is horizontal, k is vertical, no different. That's the parent, a over x. And your asymptotes, that's going to be vertical, that's going to be horizontal. But again, it all comes back to if x is approaching a certain number, we notice that y is going towards positive negative infinity for vertical asymptotes, as I just said over here. And for horizontal and behavior asymptotes, as y gets really large, we notice that as x gets really large or really negative, y is approaching a certain number. So in this case, the parent function y equals 1 over x, undefined right there. And obviously, if I plug in -3, I get -1/3, -1/2, -1, 1, 1/2, 1/3. Domain we already talked about, all real, but 0. Now, if you transform, remember h is 3, k is 2, so you're going to add 3 to x, add 2 to y. So you get 0, 1, 2, 3, 4, 5, 6. Add 2 to y. You get 5/3, 3 halves, 1. Still undefined here. Can't divide by 0. Then, of course, if I add 2, I get 3, 3.5, and oh, I'm sorry. Wow, I cannot add today. 2.5, my bad, and 2 1/3. Okay. So if I plot these points, 0, 5/3, 1, 3 halves, 2, 1. There's a vertical asymptote right here. 4, 3, 5, 2.5. So the graph's going to look something kind of like this. I'll do a different color here, do green. So our asymptotes are going to be at y equals 2 and x equals 3. Now, again, you could memorize this h and k. If you do, I will not be very happy, because you have to understand why is it y equals 2. As x approaches positive or negative infinity, y is approaching 2. It's pretty obvious. Make x really big, it's going to get really close to 2. Make x really negative, going the other direction, it's still going to be approaching 2. Why is this happening? As x approaches 3 from the right or the left, I put a little superscript as plus or minus, y is approaching positive or negative infinity, which is very true. If I get very, very close to 3, we're going to notice, like if you're putting like 3.1 or 2.9 or 2.99 or 3.101, that's what's going to happen, is that you're going to notice that y is getting bigger or more negative. That's a real reason why. That's what we have to look at. So in this case, we'll make a little table. Horizontal and vertical. Horizontal, obviously, are y equals. Vertical, of course, is x equals. Remember, x equals is a vertical line, right? Y equals a horizontal line. So clearly we are shifting the graph one left. So that makes that the vertical asymptote switches one left. Here we're going two left. You're going two right. So that causes the vertical asymptote to switch. Then of course we're going down two. So horizontal asymptotes now -2, up 3, or up 5. So we'll actually do a little more explanation of this next time in class. So that kind of covers all the stuff here for asymptotes as well as simple rational functions. We'll do some practice in this packet when we meet again as a class. Okay, we're all set.